Good day, sir. We are from group 11, and our presentation is about proton exchange membrane fuel cell (PMFC). And the group is consisted of Clinton Anna bin Shashudin at 6375, Daniel Harris bin Habiri at 2503, Felix Nian Anna Vincent at 2563, and Ho Yi Hang at 2587. I'm Ho Yi Hang, and I'll be presenting the working principle of PMFC. So, at the anode side, the hydrogen is separated into hydrogen ions and electrons. Meanwhile, for the cathode side, the hydrogen ions will react with electrons and oxygens to produce water and heat through oxygen reduction reactions. The role of electrolyte in PMFC is to conduct proton from the anode to the cathode while blocking electrons and gases. The flow of electron is shown in the figure below, where it is conducted from anode to cathodes.
Hello, my name is Daniel Harris, matrix number 82503, and I will be explaining about the figure and the list of labels for our proton exchange membrane fuel cell. So based on the figure above, the main basic components of a PEM fuel cell include the anode and cathode, electrolyte, and the catalyst. The anode is the negative electrode where the hydrogen gas is fed. The cathode is the positive electrode where the oxygen gas is fed. Now, the electrolyte is a proton conducting membrane that only allow the proton to pass through it while blocking electrons. And the catalyst, usually made out of platinum, is used to speed up the reaction at the electrode. Based on the figure, it represents a single cell of PEM fuel cell. And the next black and white figure is how a stack of cells are usually like. At the core of the PEM fuel cell is the MEA or membrane electrode assembly, which is formed by two catalytic materials that act as the anode and the cathode electrode, separated by the PEM or the proton exchange membrane. Usually, commonly, platinum presents high catalytic activities, stability and durability, and selectivity for the cathodic reaction in the energy conversion device.
Next, the technical advantages of PMFC. In terms of transportation, it has high energy density, quick refueling and startup, as well as it's a clean energy. Then, for portable power, it has a long operation time, less charging time, it's lightweight and compact. Then, for stationary power, it's clean, efficient, and reliable for power generation, which is independent of the grid connection. For airspace and underwater, it has long endurance, and is widely applied in this application.
As for the challenges, there are four main issues. First is high cost. These fuel cells are expensive mainly because the use of platinum catalysts, which are costly and limited in supply. Currently, the cost of PEMFC system is around $75 per kilowatt, even at high volume production. However, the US Department of Energy has set more aggressive targets of $30 per kilowatt for light-duty vehicles and $60 per kilowatt for heavy-duty vehicles, indicating that further cost reduction is still required. Second is limited durability. Fuel cell components degrade over time due to temperature changes, humidity variation, impurities, and frequent start-stop operations. So these will reduce the lifetime of PEMFC systems, especially in transportation applications. Currently, these fuel cells typically achieve about 5,000 hours of operation in transportation application. However, the target durability is at 1,000 hours for transportation, highlighting the need for improved materials and better system design. Third is water management issues. Water is necessary for fuel cell operation, but too much water can cause flooding, while too little water can cause membrane drying. So poor water control lowers performance and shortens the fuel cell lifetime. Finally is the hydrogen storage and distribution. Producing, storing, and transporting hydrogen is expensive and technically challenging. So in addition, the lack of refueling infrastructure limits the widespread use of PEMFC. Next, I will be presenting the material selection at the electrode. So before that, my name is Felix Anna Vincent with the matrix number 82563. So the material selection is influenced by the electrolyte use in the fuel cell as it defines the operating temperature, humidity requirements, and also the acidity. So the first electrolyte that has been used in this fuel cell is perfluorosulfonic acid, PFSA membranes, such as Nefion. So these conditions operate at 60 until 80 degrees Celsius under humidified and strongly acidic conditions. So in this environment, platinum or platinum alloy catalysts supported on carbon are required at both the anode and cathode to ensure sufficient catalytic activity and also the stability. Material selection and electrode design therefore focus on optimizing alloy composition, improving carbon support durability against corrosion, and tolerating the PFSA inomer contact. Next, the Second electrolyte is the hydrocarbon-based proton exchange membranes, including sulfonate poly and sulfonate polymide. So the operating temperature in this kind of electrolyte is generally higher, which is around 80 until 120 degrees Celsius, and it often at lower relative humidity compared to the PFSA systems. Although the same platinum or platinum alloy carbon catalysts are typically employed, the different chemical nature or hydrocarbon enormous significantly affects catalyst layer wetting behavior and susceptibility to interfacial poisoning. So as a result, both anode and cathode catalyst layer must be re-engineered, including adjustment to catalyst informulation, enamel type, and also the electrode processing methods in order to maintain performance and durability compatible with the membrane chemistry. So the last electrolyte is the phosphoric acid dope polybenzimidazole, or known as PBI. So the electrolyte operates under anhydrous conditions at elevated temperature, which is around 120 until 200 degrees Celsius, in the presence of concentrated phosphoric acid. So these harsh conditions necessitate higher platinum loadings at both electrodes, typically using platinum or platinum alloy catalysts supported or more graphitic or nanofiber carbon materials to improve resistance to carbon corrosion and acid attack. So additionally, this kind of electrolyte are employed instead of PFSA anomers, and PTFE content is carefully tuned to manage acid distribution and maintain electrode integrity over long-term operations.
Hello and good day everyone, my name is knc4283 Samsudin and I will be presenting the operation temperature and efficiency part. From this slide we can see there is a graph which is I obtained from a journal shows that how different temperature affect the performance of PEM fuel cells. Now at low temperature between 65 to 70 Celsius, we can see it represented by the black and the red line in the graph. We can see that at the lowest amount of voltage at the end, the performance produces the lowest amount of current density. Why? Because hydrogen oxidation at the anode is lower. Second, oxygen reduction at the cathode is sluggish. This causes the proton transport through the membrane is less efficient. Hence, this result the higher internal losses and faster voltage drop as current increases. Now, at medium temperature, 75 to 80 Celsius, we can see from the graph it represented by dark blue and green line. What happened during this temperature is that hydrogen splitting reaction become faster, proton conductivity of the membrane improve, and oxygen transport is more effective. Hence, the result on this performance is that highest voltage at the same current density, slowest voltage drop with increasing current, and maximum current density before voltage collapse at the highest temperatures, which is 85 Celsius, represented in the graph with light blue line. What happened during this temperature is that hydrogen oxidation and oxygen reduction reactions are very fast. Proton transport through the membrane is highly efficient. Oxygen diffusion to the cathode catalyst is enhanced. However, result of the performance, although it's reduced voltage losses, more stable voltage over wider current range and higher achievable current density than low temperature. At higher temperature, the performance of PEM fuel cells tends to degrade faster due to membrane dehydration. And that's why during the highest temperature, which is 85 Celsius, the total current density, the maximum current density is still lower than the medium temperature. Thank you.